In this DL, we did some amateur optometry. A super important part of optometry is using lenses to correct vision. To see how this works, let's consider this simple model of an eye. We have an object right here and the eye right here. Light leaves this object and passes into the eye. The lens of the eye focuses those light rays onto the retina at the back of the eye, which then sends signals to the brain, which can be interpreted as an image. If you have so-called perfect vision, aka 20/20 vision, you probably don't think at all about this. One thing that makes our eyes so special is that they're able to focus on things at different distances away. Right now, I am looking at my camera, and my eyes are focused on the camera, but the background is blurry. I can't really make out all the details. However, if I now shift my focus to the background is clear while the camera is blurry. Our eyes do this by actually adjusting the focal length of the lenses in our eyes. If this is working perfectly, it works so well that we don't even notice it's happening. However, for many people, this does not work quite as intended. It turns out that we can correct this by adding a second lens in front of the eye. However, before we can figure out which kind of lens we can use, we have to determine what the issue is. Generally, we break up vision issues of this kind into two broad categories: nearsightedness and farsightedness. An individual who is nearsighted is able to see objects that are close to them without issue, but has a hard time focusing on objects that are far away. Whereas an individual with farsightedness is able to focus on objects that are far away without difficulty, but is not able to focus on objects that are nearby. When we correct vision, we are trying to make it so that these individuals are able to see the objects that appear blurry without the corrective lenses. To do this, we're going to need to define a standard. In other words, a range of distances over which we want all individuals to be able to focus if they're wearing their corrective lenses. For individuals with 20/20 vision, the closest they can generally focus on something is about 25 centimeters. That's about this far. Any closer and our eyes have to strain in order to focus on what's in front of us. But holding my hand like this, I am able to focus on it without difficulty. In principle, someone with perfect vision should be able to also focus on objects that are infinitely far away. There is no farthest point that they should be able to focus on. So let's start with the case of farsightedness. In other words, where an individual has no problem focusing on very far things, but has a hard time focusing on near things. Let's suppose that the closest that an object can be, such that this individual can actually focus on it, is 60 centimeters. We can immediately see why this would be a problem. Suppose you were trying to read a book, but you had to hold the book 60 centimeters away from your face at all times. That's probably a lot more frustrating than just holding it like this. So how do we fix this? Well, let's think about how lenses work in a two-lens system. A lens is not able to tell the difference between a physical object and the image of that object produced by another lens. So how might we correct this vision? What if we use a lens such that if we take an object and hold it 25 centimeters away from the lens, the image that is formed by the lens appears to be 60 centimeters behind the lens. The eye of the person wearing the corrective lenses can't tell the difference. An image at 60 centimeters appears the same to the eye as an object at 60 centimeters. Because this individual is able to focus on objects that are 60 centimeters away, this will work. They will be able to see the object even when it's held up close. Let's try to determine what the focal length of the lens needs to be such that we're able to correct this vision. The object is going to be 25 centimeters away, while the image is going to be 60 centimeters away. But is the distance to the image a positive or a negative number? Well, we know that when an image is on the same side of a lens as an object, that image is a virtual image. Virtual images have negative distances. So let's plug the image distance and the object distance into the thin lens equation. All we have to do is solve this equation for f. I get that f is 42.8 centimeters, but let's just call that 43. We found that if an individual is unable to focus on any object that is closer than 60 centimeters away from the eye, and we want them to be able to focus on things that are 25 centimeters away from the eye, then we need a lens with a focal length of 43 centimeters in order to do this correction. Now you may be asking, but doesn't this mean that the object will appear smaller? After all, if the image of the object appears farther away, it should seem smaller. But not so fast. Remember the magnification equation. It just says that the magnification of the image is equal to the negative image distance divided by the object distance. Let's just plug that in. The image distance is just negative 60, and the object distance is just 25. So the image will appear to be farther away than the object, but it will also appear to be significantly larger. Also notice that this magnification is positive. The negative sign here and the negative sign on the image distance cancel out to form a positive. This makes sense. We want the image to be right side up. Now let's think about nearsightedness. Nearsightedness is exactly the opposite problem. It's possible to focus on things that are close by, but not possible to focus on things that are far away. Let's say that this individual cannot focus on any object that is farther than 5 meters away. How might we correct their vision so that they're able to see more distant objects? We can do this by creating an image of distant objects at that far point. In other words, if an object is an infinite distance away, we want the image of that object to appear 5 meters away. Any object that is closer than infinity will appear a little bit closer than 5 meters, but the person should still be able to focus on it just fine, because they're able to focus on things that are close. So let's plug in the numbers and see what we get. We want the image to be 5 meters away. However, this is still a virtual image. The image is on the same side of the lens as the object, so this distance has to be negative. But what about the object distance? Well, we said that we want objects that are an infinite distance away to appear 5 meters away. For the object distance, we'll just plug in infinity. But what's 1 divided by infinity? Well, it's just 0, so we don't have to even include this in our equation. So what's the focal length of the lens we need? Well, we can just solve this equation for f by flipping both sides. Notice immediately there's a difference between this result and the result for the farsighted case. The focal length of the needed lens here is negative, whereas the focal length of the lens in the other case was positive. A negative focal length corresponds to a diverging lens, while a positive focal length corresponds to a converging lens. So not only are the focal length of the needed lenses different for the two cases, the type of lens is different for the two cases. For reasons that I'm not aware of, we generally do not talk about focal length when we're talking about corrected lenses. Instead, we talk about something called the optical power of the lens. We measure optical power in units of diopters, but it turns out that there's a very simple relationship between focal length and optical power. The optical power of a lens is just 1 divided by the focal length of the lens. So the optical power for the nearsighted correction is negative 0.2 diopters, and the optical power for the far-sighted correction is 2.3 diopters. One thing to note is that whenever you're looking at optical power, you have to know the focal length of the lens in meters. When we did the far-sighted case, we originally calculated the focal length in centimeters. We found that the focal length for this lens was 43 centimeters. This corresponds to a focal length of 0.43 meters. This result, though, is fairly general. For individuals who are far-sighted, we want to push the image of an object farther back to allow them to see it. We do this using a converging lens with a positive focal length. However, for individuals that are nearsighted, we need the opposite effect. We want objects that are very far away to appear closer so that the eye can focus on it. And so we need a diverging lens. Now, I would like to point out that this DL is not a replacement for an optometrist. They know how to test your eyes much better than you can at home. So you should always take their advice on which prescription to use. Next DL is going to kind of feel like a complete left turn. We started looking today at static electricity. Next DL, we're going to start our study of electricity and magnetism in earnest, and that will carry us on through the rest of the quarter.